Hey there guys, Paul here from theengineeringmindset.com. In this video, we're going to be learning how star-delta starters work for three-phase induction motors. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. Now this is a real-world star-delta starter, and by the end of this video, you'll be able to tell me what each part does and how the whole system works together. We have an electrical terminal box. I'll just move that box here to make it easier to see. Inside this electrical terminal box, we have 6 electrical terminals. Each terminal has a corresponding letter and number. We have U1, V1 and W1, and then W2, U2 and V2. We have our phase 1 coil connected to the 2 U terminals. We then have the phase 2 coil connected to the 2 V terminals. And then we have the phase 3 coil, which is connected to the 2 W terminals. Here's a real-world example of an induction motor's electrical terminal box. Now I'm going to test your understanding of this a little later into this video. Notice that the coil terminals are in a different arrangement from the top side to the bottom side. We'll see why that is in just a moment. We now bring in the 3-phase power supply and connect these to their respective terminals. We always connect the supply side to terminals U1, V1 and W1. Now for the motor to run, we need to complete the circuit, and there are 2 ways to do this. The first way is the delta configuration. For this, we connect across the terminals from U1 to W2, V1 to U2, and W1 to V2. This will give us our delta configuration. Now when we pass an AC current through the phases, we see that electricity flows from one phase into another as the direction of AC power reverses in each phase at a different time. That's why we have the terminals at different arrangements, because we can connect across and allow electricity to flow between the phases as the electrons reverse direction at different times. Now the other way that we can connect the terminals is to use the star configuration. In this method, we connect between W2, U2 and V2 on only one side of the motor terminals. This will give us our star equivalent design. Now when we pass AC current through the coils, we see that the electrons are shared between the phases at the terminals. The 2 ways we just saw of configuring the motor in star or delta are fixed methods. To change them, we have to physically cut the power, open the motor terminals, and then rearrange them. Now this isn't exactly practical to do. So how can we automate this? To do this, we need to use some contactors. Now they come in various designs, but if we look inside one, then the basic operation is just a switch that can either make or break a circuit to control the flow of electricity in all 3 phases simultaneously. So we take our main contactor, and then we connect our 3-phase supply to one side, and then we connect the other side to the respective terminals within the induction motor's electrical terminal box. We then take a second contactor, which will be used for our delta circuit, and we feed our 3 phases into this also. From here we connect our phase 1 to terminal V2, which is the phase 2 coil. Then we connect our phase 2 to terminal W2, which is the phase 3 coil. And finally, we connect our phase 3 wire to the U2 terminal, which is the phase 1 coil. Now we take another contactor, which will be used for our star circuit, and we connect our 3-phase power into this. On the top, we just connect all 3 phases together. I'll just remove the casing of the contactors so that we can see what's happening inside. Now we start in the star configuration, and to do that we activate both the main and the star contactor terminals so that they close to complete the circuit. Now when we pass electricity through the circuit, the electricity passes through each phase and coil and then out through the motor terminals and into the star contactor where the path of the electrons is shared. This allows them to flow in and out of another phase as the direction of each phase changes. This star connection method will run for a few seconds before switching over to delta. For the delta connection, we disconnect the star contactor and then close the delta connection. This all happens very quickly. Now we have the electricity flowing in, but it splits direction. It flows into both the main as well as the delta contactor. The electricity in the main contactor path will flow into the motor coils, and the electricity which took the delta contactor route will flow to the opposite side of the motor terminals. Each will then flow between the different phases as they reverse direction. To control the changeover from star to delta contactors, we simply use a timer to control this. This will automatically change the configuration over after a set amount of time. Additionally, there are more advanced versions which will monitor the amps or motor speed. This is an old, outdated color system, but old installations are still going to exist. So coming back to this real-world photo of a star-delta starter, can you tell me which part is which? 3, 2, 1, Correct. This is the main contactor, this is the delta contactor, this is the star contactor, and this is the timer. Notice on the star contactor, they've just connected two wires into the same terminal to create that star point. So why then do we use star delta starters? We use the star delta starter to reduce the inrush current when the motor starts. When a large induction motor starts in delta, their starting current can be over 5 times higher than the full load current which occurs when the motor stabilizes and runs normally. This huge surge in current will cause lots of problems. The building's electrical system will be hit by this sudden large demand. The electrical infrastructure will rapidly increase in temperature, leading to component failure and even electrical fires. The sudden large demand causes voltage drops throughout the building's electrical system. This can be visually seen because the lights will dip. This can cause many problems for sensitive equipment such as computers, servers, and safety systems. So to reduce the starting current, we simply need to reduce the starting voltage. The star configuration will reduce the coil voltage to around 58% compared to the delta configuration. A lower voltage will lead to a lower current. Current in the coil, while in star configuration, will be around 33% of the delta configuration. This will also lead to a reduction in torque. The star configuration torque will also be around 33% compared to delta. So let's look at a simplified, basic example of what's happening here to understand it further. Now let's say we have the motor connected in delta with a typical European supply voltage of 400 volts. That means when we use a multimeter to measure the voltage between any two phases, we will get a reading of 400 volts. We call this our line-to-line voltage. Now if we measure across the two ends of a coil, we again measure the line-to-line voltage of 400 volts. Let's say each coil has a resistance or impedance, as this is AC power, of 20 ohms. That means we will get a current reading on the coil of 20 amps. We can calculate that from 400 volts divided by 20 ohms, which equals 20 amps. But the current in the line will be different. It will be 34.6 amps, and we get that from 20 amps divided by the square root of 3, which gives us 34.6 amps. That's because the phase is connected to the two coils. Now if we look at a star configuration, we again have a line-to-line voltage of 400 volts, and we see that if we measure between any two phases. But with the star configuration, all our coils meet at the star point or the neutral point. It's from this point that we can run a neutral line if we need to. So this time, when we measure the voltage across the ends of any coil, we get a lower value of 230 volts. That's because the coil isn't directly connected between two phases like the delta version was. One end is connected to the phase, but the other end is connected to the shared point or the neutral point. So the voltage is therefore shared and will be less because one phase is always in reverse. We can see the 230 volt reading by dividing 400 volts by the square root of 3, which gives us 230 volts. As the voltage is less, the current will be too. If the coil is again 20 ohms of resistance or impedance, then the current is calculated by 230 volts divided by 20 ohms, which is 11.5 amps. The line current in this design will also therefore be 11.5 amps. So we can see with the delta connection, the coil is exposed to the full 400 volts between two phases. But the star connection is only exposed to 230 volts between the phase and the neutral point. So we can see that the star uses less voltage and therefore less current compared to the delta version, and that is why we use it first. Okay guys, that's it for this video, but to continue your learning then check out one of the videos on screen now and I'll catch you there for the next lesson.